Hi ladies and gentlemen, this is Miss Skokin. We're going to start a unit on conic sections, and if you remember from class, we took a cone and we sliced it in different ways, and that slicing gave us the different conic sections. So we're going to take a look now at some skills that are going to help us with this unit in conic sections. To start with, we're going to be solving for y. Turn the video back on when you have finished solving for y in these two equations. Hopefully you didn't have any difficulty with those. Remember that when you impose that radical symbol to take the square root of both sides, anytime you're doing an even root, you need to have that plus or minus. That plus or minus is going to give you a specific shape on our coordinate plane when we graph it. It means you're going to have a top half and a symmetrical bottom half. Okay, so for objectives, recognize conic sections as intersections of planes and cones, and we've already gotten a head start on that with the activity that we did in class. And then use the distance and midpoint formulas to solve problems. So this is great. These are both things that we're familiar with, and we're going to get our memories refreshed. The only new vocabulary for right now is conic section. And you can see here a diagram that does the same type of slicing of the cones, of the double cones, that we saw in class. And just a note, as you take a look at the graphs of these, you can see what the shapes are: circle, ellipse, parabola, and hyperbola. And hopefully you've noticed that the only one of these four that is a function is the parabola. The others are relations, but they are not functions because there are multiple y's for some of the x's that are used. This means when we're graphing either by hand or on a graphing calculator, we're going to have to consider both the positive side and the negative side, the top half and the bottom half of these, and you can see they're symmetric on the top half and the bottom half, which makes sense. This is going to be where we have a plus or minus out in front of the relation. Okay, so a circle we are familiar with. It's defined by its center and its radius. An ellipse is kind of like a squashed circle. It's elongated. And instead of having an infinite number of lines of symmetry as a circle does, it's going to have two perpendicular axes that are different lengths. That's what makes it, and these are lines of symmetry, these two axes. That's what makes it an ellipse versus a circle. So a circle is a special case of an ellipse. All right, so let's take a look at an example. We want to graph this on the graphing calculator, and in order for us to do that, we're going to need to solve for y. And then once we graph it on, or the way that we're going to graph it on the graphing calculator, we're going to solve for y, we're going to put it in as two separate functions. We want to know what the shape is, so we're going to identify what type of conic section it is, and then we're going to describe the center and the intercepts. So you can see the title is Graphing Circles and Ellipses on a Calculator, so you know it's going to be one of those two. So try to solve for y first, and then put it into your calculator as two separate functions, the top half and the bottom half. You can see here when you solve for y what you end up with. So the next step is to put it in the calculator. First the positive version, so 1 plus the square root, blah, blah, blah. The other one is going to be 1 minus the square root. So we'll take a look at that next. Okay, the other thing that you need to remember on this is so that the shape looks like it's supposed to look, you're actually going to do a zoom square on the calculator. And you can see what this circle looks like. Hopefully yours on your graphing calculator looks exactly the same. And you can see where the center is using your trace key. And you can see where the intercepts are of this circle. And you can see that it has a radius of 1. All right. So we can look at the table, and remember we look at the table by doing second graph, and it shows us that we can find the intercepts very easily. When x is 0, we have the y-intercept, and when y is 0, we have the x-intercept. Okay, we have another example here. So once again, you're going to be solving for y. Turn the video back on when you're ready to check the result. Okay, once again, solving for y gives you a top half and a bottom half because you have that plus or minus. Now let's see what it looks like on the calculator. We've put it in as two separate functions under y1 and y2. We can see that it's this elongated shape, and you can see that it's centered on the origin, and you can see with either using the trace key or counting that the intercepts On the x-axis, the x-intercepts are -5 and +5, and on the y-axis are -2 and +2. We can also see that on the table. Just a quick comment on the ellipses. We saw an example that was longer on in the x in the horizontal direction, but they can go the other way also, where they're tall and skinny. And they do not need to be centered as circles don't need to be. They do not need to be centered on the origin. They can be centered somewhere else. Okay, let's talk about parabolas. Parabolas are single curves, meaning there are not two branches as we see in the hyperbolas. Hyperbolas have two branches that are congruent. They're the same size and shape. They're symmetric to one another. The parabola also has a line of symmetry, and the parabola can, the parabolas we've seen up to now either open upward or open downward, but the parabolas that we're going to see in this unit can also open to the left or open to the right. The parabola will either have an x squared term or a y squared term, but not both. But all the other conics will have both an x squared and a y squared term. Okay, let's take a look at this example. We want to, just as we did before with the ellipses and circles, we're going to be graphing parabolas and hyperbolas on our graphing calculators. So you're going to need to solve for y, and you can see that this is a parabola. This is not a shape that we're unfamiliar with. This is something that we studied in the previous, I believe it was chapter 2. And so this time we're going to graph it, identify the conic section, describe the vertices. Remember, parabolas have a vertex, either a maximum, a minimum, and now with the new types of parabolas, we're going to see it can be the or left or right as well, and the direction that the graph opens. So we're already solved for y, so this one can go straight into the calculator. And when we put it into the calculator, you can see it's downward facing. It has a vertex at 0, 0, and it has been vertically compressed by a factor of 1/2. All right, here's another example. Remember, we need to solve for y so that we can put it in the graphing calculator under the y1 or y2 or both. And then we're gonna, once we solve for y, oops, sorry about that. Once we solve for y, and you can see here we have the plus or minus, so we know that there's going to be a top half and a bottom half. We're going to put that in the graphing calculator, and let's see what it looks like. Ooh, it's a hyperbola. And you can see a hyperbola is also, it has an axis of symmetry, and it has multiple actually axes of symmetry. You can see that we have two vertices, not just one, and they are at +3 and -3. And they are on the y-axis. I'm not sure, you may have a couple of other examples in your notes. If you do, go ahead and get those done, and we will check those in class. As promised, we're going to review the midpoint and distance formulas. They're going to help us find the center and radius of a circle. So remember that the midpoint formula, what we're going to do is find the average of the x's and find the average of the y's, and the midpoint is going to be those two averages as an xy pair. With the distance formula, it's that idea of the Pythagorean theorem between the 2 points, dropping a perpendicular straight down from one point and driving the horizontal to until we form that 90-degree angle, and then we have a hypotenuse between the 2 points. This allows us to find the distance, kind of the shortest distance between 2 points, they say, is a straight line. So it's not to do the horizontal and the vertical distance, but straight across a diagonal. Anyhow, so here we're finding the difference between the x's and squaring, adding to that the difference between the squared difference between the y's, and then finding the square root of that. And we'll see how we're going to use it in just a second. Okay, we know a diameter goes through the center of a circle, and we know that the midpoint of the diameter is the center of the circle. That's kind of the definition of diameter. It goes through the center. We know a radius is half of the diameter. So you can see how this kind of sets us up to be able to want to use the distance formula and the midpoint formula to find what we want to find. And we have an example. Find the center and radius of a circle that has a diameter with endpoints 5, 4 and 0, -8. So think about what makes sense to do first. And if you thought to yourself, well, finding the midpoint between those two endpoints of the diameter so that we can find the center, you're exactly right. So do that and turn the video back on when you're ready to check your answer with the coordinates of the center of the circle. Okay, so the center of the circle is at 2.5 comma -2. The next thing that we want to do is to find the radius, and that means you're using the distance formula to do it. So try to find the radius of the circle. Turn the video back on when you're ready to check your answer. Now, of course, we only needed to use one of the endpoints of the diameter and the midpoint, the center, in order to find the length of the radius. So once we do that and we find the radius, we can also check with using the other point and the distance formula along with the center to determine if we are correct or not. We check ourselves with the other point and we find the same exact radius. In the next section, we're going to continue to see the midpoint formula and the distance formula when we talk about circles, but for now you've gotten a good introduction to conic sections, and I'll see you back for section 12.2.